A shift in trajectory is underway, and our planet may be its intended destination. The interstellar traveler, designated 3 Atlas, once presumed to be a mere celestial vagrant, has begun a subtle yet persistent acceleration on a path previously thought impossible. Independent analyses, building upon Avi's findings of non-gravitational acceleration near its closest approach to the Sun, indicate that if this push continues for just 50 days, its speed could increase by 86 meters per second. This alteration is significant enough to align its course with Earth on December 19, 2025. The critical question remains: is this a consequence of natural forces or a deliberate act of propulsion? Is it merely an interaction of dust and sunlight or a calculated maneuver? Concurrent with this observed motion, a peculiar signal has been detected, a frequency of 1.44 gigahertz. These faint, rhythmic pulses, almost mathematical in their cadence, echo through the vastness of space, suggesting a response. Could this be a form of communication or coordination? Join me as we delve deeper, because by the conclusion of this presentation, you will comprehend why some of the world's most astute scientific minds are contemplating an extraordinary possibility. 3 Atlas is not simply passing by. It may be actively navigating toward us. If this enigma has captured your intrigue as it has mine, please consider expressing your engagement by liking this video and subscribing to Cosmo Chill to ensure you do not miss any updates as this unfolding narrative progresses in real time. Share your thoughts in the comments below, indicating your location, the current time there, and your perspective on this developing situation. Furthermore, to bolster this community's reach, consider sharing this video across platforms like X, Facebook, Reddit, or even within your personal group conversations. Your support is the driving force that enables us to pursue and uncover stories such as this. Therefore, I extend my sincere gratitude for your steadfast backing. Part 1. Examining the assertion. A visitor is approaching. Currently, somewhere between the orbits of Mars and Jupiter, an entity originating from beyond our solar system is traversing its expanse. This is not conjecture. It is not science fiction. The object is demonstrably real and has been assigned the identifier 3 Atlas. Its detection occurred on the 1st of July, 2025, by the Asteroid Terrestrial Impact Last Alert System situated in Chile. What elevates this object beyond the ordinary is not merely its extraterrestrial origin. Its significance lies in its current perceived activity. A series of communications emerged on X, the social media platform formerly known as Twitter. An independent researcher presented a calculation that commanded considerable attention. The essence of this claim is as follows. If 3 Atlas were to maintain a non-gravitational acceleration of approximately 0.02 millimeters per second squared for a period of roughly 50 days, it could achieve a change in velocity of approximately 86 meters per second. This calculated velocity change, according to the assertion, could position the object to intercept Earth's orbital path around December 19, 2025. To reiterate, the claim suggests a potential alignment with Earth. The discourse extended further, positing that this alignment might not be accidental, but rather the result of deliberate maneuvering. The claim also referenced 1.44 gigahertz signals, interpreted as potential communications, and even suggested a form of inter-object dialogue between an alien probe and an entity near Mars. Before dismissing this as merely another fringe theory, let us examine the established facts. The object's existence is confirmed. Its orbital path is hyperbolic, signifying it is not gravitationally bound to our Sun. It originated from interstellar space. Its closest approach to the Sun, known as perihelion, occurred around October 30th, 2025. Crucially, reports do indeed indicate the presence of non-gravitational acceleration. This implies the object is exhibiting motion that cannot be solely attributed to gravitational forces. Non-gravitational acceleration is not an inexplicable phenomenon. It is a manifestation of physics, perhaps not fully understood within this specific context. When an object in space deviates from its predicted gravitational trajectory, an external force must be at play. Typically, this force originates from outgassing. Comets frequently exhibit this behavior. As ice vaporizes, it creates jets of gas that propel the object with a minute thrust. While 0.02 millimeters per second squared may seem insignificant, it is approximately 150,000th of Earth's gravitational acceleration. However, in the vacuum of space, over extended periods of days and weeks, even minor propulsions can accumulate. The situation becomes more compelling when considering that this is only the third confirmed interstellar object ever detected. The first was Oumuamua in 2017, a cigar-shaped anomaly that fueled extensive speculation. The second was Borisov in 2019, which appeared as a conventional comet. Now we have 3 Atlas, and unlike its predecessors, its behavior is provoking serious and potentially unsettling inquiries. What are the implications? If this is simply an unusual comet, it still represents a significant scientific discovery, offering a glimpse into planetary formation processes in other star systems as it traverses ours. However, if the acceleration is indeed intentional, if this object is being actively steered, then we are confronting a fundamentally different category of event. We must consider the possibility, however remote, that we are observing an engineered artifact from an extraterrestrial civilization. Our objective with this investigation is straightforward. We will meticulously scrutinize the claim, examining the supporting data, the underlying assumptions, the mathematical calculations, and any speculative extrapolations. We will differentiate between established knowledge and informed conjecture. Furthermore, we will anticipate the developments expected in late 2025 and early 2026, when further observations may either substantiate or entirely invalidate this hypothesis. This endeavor is not intended to foster alarmism. It is aimed at discerning what is factual, what is plausible, and what constitutes mere background noise. The reality is that space is replete with phenomena we are yet to comprehend. Periodically, something emerges that challenges our existing models. 3 Atlas might be such an object, or it might simply be a comet of interstellar origin exhibiting outgassing patterns that appear unusual to us. By the conclusion of this exposition, you will be equipped to contemplate a crucial question. Is this a natural comet, an alien probe, or something else entirely? You will possess the tools to form your own informed judgment, understanding the science, the mathematics, the observational strategies, and the broader ramifications. You will also know what to monitor in the coming months. Our investigation is structured in 3 distinct segments. The initial act will present the claim and the foundational data. We will explore the nature of 3 Atlas, analyze the numerical evidence, and examine the assumptions underpinning the proposed Earth intercept scenario. The second act will delve into more profound speculations, addressing controversies, exploring natural versus unconventional explanations, and investigating the social media narratives that have amplified this story. The third act will broaden our perspective, incorporating recent advancements in space science, artificial intelligence, and radio astronomy to connect 3 Atlas to the forefront of scientific discovery. We will then conclude by outlining future expectations and areas requiring your attention. One final point before we proceed. The universe operates independently of our comfort or readiness for its revelations. For the majority of human history, we harbored a belief in our solitude, considering Earth the focal point of existence, with the cosmos revolving around us. Every significant discovery since then has served as a lesson in humility. We learned that Earth orbits the Sun, that our Sun is but one among billions, and that galaxies stretch beyond enumeration. Now, we are learning that objects from distant star systems can visit us. What transpires when one of these visitors exhibits behavior that defies easy explanation? In the subsequent section, we will examine the empirical data to enable you to ascertain whether this claim holds scientific merit or dissolves under closer inspection. Part 2. The empirical evidence. The discovery of 3 Atlas occurred on the 1st of July, 2025. The Asteroid Terrestrial Impact Last Alert System, a network of telescopes in Chile established for detecting near-Earth objects, identified an anomaly. Initially, it appeared as an unremarkable faint point of light traversing the sky. However, subsequent orbital calculations revealed something extraordinary. The object's trajectory was hyperbolic. A hyperbolic trajectory signifies that the object is not gravitationally bound to the Sun, moving at a velocity too high to be captured by the Sun's gravity. It originated from an external source, passed through our solar system, and is destined to depart back into the vastness between stars. This characteristic is the definitive hallmark of an interstellar visitor. The designation 3 was assigned, marking it as the 3rd confirmed interstellar object. Let us consider its orbital parameters. Perihelion, the point of closest approach to the Sun, was reached around October 30th, 2025. The distance at this point was approximately 1.36 to 1.4 astronomical units. 1 astronomical unit represents the average distance between Earth and the Sun, approximately 150 million kilometers. Therefore, at perihelion, 3 Atlas was situated between 203 and 210 million kilometers from the Sun, roughly within the orbital radius of Mars. Its closest predicted approach to Earth is scheduled for December 19th, 2025. At this juncture, the distance will be approximately 1.8 astronomical units, translating to roughly 268 to 270 million kilometers. For context, the Moon is approximately 384,000 kilometers from Earth. This object will pass at a distance equivalent to about 700 times the Earth-Moon separation. This is a considerable distance, far beyond any conventional definition of a near miss. Now, we turn to the anomaly. In a publication on Medium, Avi Loeb, the renowned Harvard astrophysicist known for his work on Oumuamua and the search for extraterrestrial intelligence, reported an unusual observation. Astrometric data acquired by the Jet Propulsion Laboratory and the Atacama Large Millimeter Array indicated a deviation from the predicted path. The object's position was not consistent with what gravity alone would dictate. This positional offset measured approximately 4 arc-seconds, a minuscule angular shift, but one that is significant when tracking an object across millions of kilometers. Loeb's calculation resulted in a non-gravitational acceleration of approximately 0.02 millimeters per second squared. He then employed a momentum conservation equation to explore potential causes. If outgassing is the driving mechanism, meaning jets of vapor emanating from the object are providing the impetus, then the rate of mass loss would need to be substantial. His calculations suggested that at least 1/16 of the object's mass would need to sublimate over approximately 1 month to generate this level of acceleration. Let us pause to consider this. While this rate of mass loss might seem extraordinary, comets routinely experience it. When ice transitions from a solid to a gaseous state, it escapes from the surface, generating a propulsive force. This is analogous to a rocket engine, albeit a weak one, but measurable. The challenge with 3E Atlas lies in the scale of this phenomenon. If the object possesses a mass as substantial as some estimates suggest, in the tens of billions of tons, then losing 1/16 of that mass within a month should result in a visibly dramatic expulsion of gas and dust, forming a discernible coma and a tail observable phenomena. Visually, 3E Atlas has displayed some peculiar characteristics. Imaging reveals a jet-like structure, potentially oriented toward the sun rather than away, which is an atypical configuration. The object's coloration has also drawn attention. Reports describe it as appearing bluer than the sun, possibly indicating the presence of ionized carbon monoxide rather than typical dust. These are indeed intriguing clues, but they are not conclusive. Comets can exhibit unconventional behaviors, and interstellar comets are even more prone to anomalies. What does the data not reveal? Loeb himself does not assert that the object is on a trajectory to intercept Earth. He does not claim it is deliberately maneuvering toward us. The data confirm an acceleration and a positional offset, strongly suggesting that something noteworthy is occurring. The extrapolation to an Earth intercept and intentional steering originates from elsewhere. It stems from the social media post that took Loeb's numerical findings and applied further calculations. Here is the crucial distinction. The raw data are compelling but not inherently inexplicable. We have a hyperbolic interstellar object exhibiting some degree of outgassing and a jet structure that, while unusual, can be accommodated within the framework of known physics. It is certainly on the unconventional side of the spectrum, but not impossible. The fundamental question is whether the data genuinely support the audacious claim that 3E Atlas is actively altering its course towards Earth, or if a real dataset has been subjected to layers of interpretation and assumption to arrive at a sensational conclusion. Thus far, our understanding is as follows. We have a confirmed interstellar object. Its trajectory brings it to a relatively close, albeit still extremely distant, proximity to Earth. There is evidence of non-gravitational acceleration, which could be attributed to outgassing or an alternative cause. And there is a mathematical calculation demonstrating how a sustained, minimal propulsive force over 50 days could result in a significant change in velocity. Does this evidence suffice to declare that the object is aligning with Earth? This is the pivotal question we will address next by dissecting the mathematical underpinnings and the assumptions that transform raw data into a compelling narrative. Part 3. Extrapolation to Earth. Intercept. Mathematics and assumptions. Let us examine the arithmetic. The assertion originating on social media begins with a fundamental equation from classical physics. Acceleration multiplied by time equals change in velocity. If an object experiences a constant acceleration of 0.02 millimeters per second squared for a duration of 50 days, what is the resultant change in velocity? 50 days equates to 4,320,000 seconds. Multiplying this by 0.02 millimeters per second squared, which is equivalent to 2 times 10 to the power of -5 meters per second squared, yields approximately 86.4 meters per second. This is the delta V, the alteration in velocity. The mathematical computation itself is accurate and not subject to dispute. Now, let us consider displacement. When a constant acceleration is applied over a period of time, it not only modifies velocity, but also alters position. The displacement under constant acceleration is calculated as 1/2 multiplied by acceleration, multiplied by time squared. plugging in the values: 1/2 times 2 times 10 to the power of -5 meters per second squared times 4.3 2 times 10 to the power of 6 seconds squared results in approximately 1.87 times 10 to the 8th meters, which is 187,000 kilometers. This is roughly half the distance from Earth to the Moon. Therefore, these numerical outcomes are indeed significant. A modest but continuous thrust sustained over 50 days could indeed shift an object's trajectory by hundreds of thousands of kilometers. In the realm of orbital mechanics, this is a substantial alteration. It possesses the potential to modify an object's crossing point of a specific orbital plane, to adjust its closest approach distance, and theoretically, to transform a distant flyby into a closer encounter. However, this is precisely where assumptions begin to accumulate. The calculation presupposes that the acceleration remains constant and uninterrupted for the entire 50-day period. Is this a valid assumption? We do not possess this certainty. The acceleration was measured at a specific point in proximity to perihelion. Whether it persists for weeks or months is unknown. Outgassing typically fluctuates in intensity based on an object's proximity to the Sun. As an object recedes from perihelion, solar heating diminishes, consequently reducing the rate of sublimation. Therefore, the propulsive force may weaken or cease entirely. The calculation also assumes that the acceleration is applied along a precisely advantageous vector. The direction of the applied force is as critical as its magnitude. If the thrust is directed perpendicularly to Earth's orbital path, it might alter the orbital plane, but would not significantly impact the closest approach distance. If the thrust is prograde, increasing the object's speed, it will affect the arrival time. Conversely, if it is retrograde, reducing its speed, the effect on arrival time will be similar. If the thrust is radial, pushing towards or away from the Sun, it will modify the semi-major axis and eccentricity of the orbit. Without definitive knowledge of the acceleration's direction, integrating the velocity change into a predictive trajectory analysis becomes speculative. Temporal alignment is another crucial assumption. The object must apply this thrust at the correct moment and in the correct orientation such that its resultant path intersects Earth's orbit precisely when Earth is present at that intersection point. Earth moves at approximately 30 kilometers per second in its orbit around the Sun, covering vast distances within days. Intercepting a moving target necessitates exacting timing and vector control. A positional shift of 187,000 kilometers might alter the point of intersection. However, if Earth is not at that location at the designated time, the intercept will not occur. Then there is the question of energy and mass. If the object is as massive as estimations suggest, tens of billions of tons, then sustaining a continuous thrust would demand an immense amount of energy. If this propulsion originates from natural outgassing, the rate of mass loss must be substantial, as indicated by Loeb's calculations. If, however, it is an artificial propulsion system, it implies a capability for sustained thrust over an extended duration. Both scenarios present considerable challenges to plausibility without corroborating evidence. Finally, we must consider the influence of gravitational perturbations. Space is not an empty void. Factors such as solar radiation pressure, the gravitational pull of planets, the solar wind, and even the Yarkovsky effect can all exert an influence on the trajectory of a small celestial body. The simplified calculation assumes these influences are either negligible or effectively average out. In reality, they introduce variability and uncertainty. A deterministic 50-day propulsion event is an idealized model. Allow me to offer an analogy. Imagine you are traveling on a highway. You are aware that you can accelerate your vehicle to achieve a speed 60 kilometers per hour faster than your current velocity. This is akin to knowing your potential delta V. However, to execute a successful lane change and reach a specific exit at the correct time requires more than just increased speed. You need to know the exit's location, the prevailing traffic speed, the opportune moment for acceleration, and the precise steering adjustments necessary. The arithmetic of velocity change is one aspect. The geometry and timing inherent in orbital mechanics represent another. The extrapolation presented on social media presumes that the observed acceleration was directed in a manner conducive to an Earth alignment. We lack any evidence to support this assumption. The data indicate acceleration, but not its specific vector relative to Earth's orbital path. The assertion then adds the interpretation that this acceleration is purposeful and Earth-targeting. This is an overlay of conjecture onto the existing data, not a direct derivation from it. Here is a summary of what we know versus what is assumed. We know that a non-gravitational acceleration is present. We know it is of small but measurable magnitude. We know the object's orbit will bring it to a relatively close proximity to Earth in December. We assume the acceleration will persist for 50 days. We assume it is directed advantageously. We assume the timing will align favorably. We assume no other external factors will interfere, and we interpret all of these assumed conditions as indicative of intentional maneuvering towards Earth. Each assumption represents a link in a chain. If even one link breaks, the entire claim crumbles. The crucial question is not whether the mathematical calculations are correct. They are. The pertinent question is whether the realities of the cosmos conform to these assumptions. In the next section, we will examine the actual trajectory and the calculated missed distance to ascertain whether a velocity change of 86 meters per second could plausibly transform a 270 million kilometer flyby into something more ominous. Part 4. Object Trajectory and Missed Distance. The official figures are unequivocal. According to NASA and the European Space Agency, 3I Atlas is projected to pass Earth at a distance of approximately 1.88 astronomical units on December 19, 2025. This translates to a range of about 268 to 270 million kilometers. To provide a sense of scale, 1 astronomical unit is the average distance between Earth and the Sun, approximately 150 million kilometers. Therefore, 1.8 astronomical units signifies that the object will be nearly double Earth's orbital distance from the Sun at its closest approach to our planet. This is not considered close. It falls far outside any standard criteria used in planetary defense. An object is classified as potentially hazardous if its orbital path brings it within 0.05 astronomical units of Earth, a distance of approximately 7.5 million kilometers. 3 Atlas will pass at a distance more than 30 times that threshold. Both NASA and the European Space Agency have explicitly stated that the object poses no threat to Earth. So, how are missed distances determined in orbital mechanics? When an object approaches on a hyperbolic trajectory, its path is dictated by its velocity, its direction of travel, and the gravitational influences it encounters. The missed distance is essentially the closest calculated point of approach based on the object's trajectory in relation to Earth's position at a specific moment in time. For 3I Atlas, this calculation yields a missed distance of 1.8 astronomical units on December 19th. Now, let us address the central inquiry. Could a velocity change of 86 meters per second significantly alter that missed distance? The answer is nuanced, encompassing both a yes and a no, depending on the context. In principle, a delta V of 86 meters per second applied over 50 days could indeed shift the object's trajectory by hundreds of thousands of kilometers. As we calculated previously, the potential displacement could be approximately 187,000 kilometers. This is not an inconsequential figure. In orbital mechanics, minor alterations in velocity can lead to substantial changes in position over time, particularly if applied early in the trajectory. However, the answer is also no, because converting a missed distance of 270 million kilometers into a direct Earth impact would necessitate a far greater delta V, unless the vector of thrust and the timing of its application were extraordinarily fortuitous. The object is traveling at approximately 60 kilometers per second, or 60,000 meters per second. 86 meters per second represents less than 0.15% of its total velocity. To modify the trajectory sufficiently to reduce the missed distance from 270 million kilometers to zero would require either a substantially larger delta V or an almost perfect alignment between the direction of thrust and the precise moment of application. The direction of the thrust is paramount. Envision the object's trajectory as a line extending through space. If thrust is applied laterally, perpendicular to the velocity vector, it will alter the orbital plane. This might result in a lateral shift of 100,000 kilometers, but it would not necessarily bring the object any closer to Earth. If thrust is applied in a forward or backward direction along the velocity vector, it will modify the arrival time. The celestial body might arrive in Earth's orbital plane sooner or later, but that doesn't guarantee a closer encounter unless Earth itself is positioned at that precise location. Adjusting the object's trajectory radially, either towards or away from the Sun, fundamentally alters the shape of its orbit, specifically its eccentricity and the closest point of approach, perihelion. Orbital mechanics employs a concept known as the B-plane, which is a hypothetical plane oriented perpendicular to an object's incoming path. This plane serves as a reference to calculate the object's trajectory relative to a designated target. Envision it as a dartboard where Earth is the bullseye. The object's path intersects this plane at a certain point, and the distance from the bullseye to that intersection defines the magnitude of the missed distance. Even a minor alteration in velocity can shift the intersection point on the B-plane. However, transitioning from the periphery of the dartboard to the center necessitates a highly specific impulse. Without precise knowledge of the direction of 3I Atlas's non-gravitational acceleration relative to Earth's current position, it's impossible to accurately determine the change in its missed distance. The prevailing claim circulating on social media presumes this impulse is favorably directed, a considerable assumption. Furthermore, the object's sheer mass is a critical factor. Current estimates indicate 3I Atlas is substantial, potentially exceeding 33 billion tons and possessing a diameter measured in kilometers. Steering a celestial body of such immense proportions via natural outgassing, which involves the evaporation of surface ice, presents a formidable engineering challenge. It's akin to attempting to guide a mountain by sublimating its frozen components. Should the propulsion mechanism be artificial, it would imply the presence of an exceptionally powerful engine or propulsion system. In either scenario, the underlying physics presents significant hurdles. Scientists from NASA and the ISA, privy to comprehensive astrometric data and sophisticated orbital models, have definitively concluded that the object is not on a collision course with Earth. Their analyses incorporate inherent uncertainties, external influences, and potential non-gravitational forces. Their models consistently predict a safe trajectory. Were the calculations to suggest otherwise, even a minor possibility of impact, it would trigger immediate widespread alerts. Planetary defense systems are specifically designed to identify and monitor objects that pose a potential threat. 3I Atlas is not currently classified as such. Therefore, a reality check regarding the missed distance reveals that the confluence of geometric alignment and precise timing renders an Earth impact scenario exceedingly improbable at this juncture. To transform a projected flyby distance of 270 million kilometers into a hazardous encounter, the object would require a considerably greater velocity change, applied in a highly specific direction and at a critical moment. While the raw numbers might appear alarming when focusing solely on the arithmetic of delta V, velocity change, the complete picture, encompassing orbital mechanics, timing, and the missed distance, unequivocally points towards a distant passage. This does not diminish the object's scientific intrigue. On the contrary, its non-gravitational acceleration, unusual characteristics, and its very nature as an interstellar visitor imbue it with considerable scientific value. However, the notion of an Earth intercept course, the assertion that it is deliberately aligning with our planet, remains firmly in the realm of speculation. Our subsequent discussion will delve into the intensifying observational campaign, the array of telescopes now focused on 3I Atlas, and the verifiable predictions that will soon elucidate whether this object is a comet, a probe, or something entirely different. Part 5. Observational Campaign and Testable Predictions. The forthcoming months are pivotal. Between the present day and early 2026, 3I Atlas will be subjected to rigorous examination. Telescopes situated across the globe and in orbit are already actively tracking its path. The object's closest approach to the Sun, its perihelion, occurred around October 30th, 2025. It is now receding from the Sun and progressing towards its December 19th close encounter with Earth. This period constitutes the crucial observation window, and it is finite. Once the object recedes beyond Earth and ventures deeper into the outer solar system, it will gradually fade from view. The primary instruments involved in this endeavor represent some of humanity's most advanced observational tools. The Hubble Space Telescope is capable of capturing high-resolution imagery across visible and ultraviolet wavelengths. The James Webb Space Telescope, with its potent infrared capabilities, can detect thermal signatures and perform detailed analyses of the composition of any surrounding gas or dust. Terrestrial observatories, including the Very Large Telescope in Chile and the KEK Observatory in Hawaii, are also contributing to this effort. Radio telescopes are actively engaged in searching for any anomalous emissions. Furthermore, closer to home, Mars orbiters may potentially capture fleeting glimpses of 3I Atlas as it traverses relatively near the red planet. An interesting celestial alignment is also anticipated. On November 4th, 2025, the European Space Agency's Jupiter Icy Moons Explorer, designated JUICE, is projected to pass within approximately 64 million kilometers of 3I Atlas. While this proximity is insufficient for a dedicated close-range flyby, JUICE's sophisticated instrumentation may still acquire valuable data from this distance. Every piece of information gathered contributes to the overall understanding. Avi and his fellow researchers have formulated a series of testable predictions which are contingent upon the origin of the non-gravitational acceleration, specifically whether it stems from natural outgassing or an alternative source. If outgassing is the causative factor, a significant mass loss would be anticipated. Loeb's calculations suggest that approximately 1/6 of the object's mass would need to sublimate over roughly a month. This process should generate a substantial envelope of gas and dust, manifesting as a visible coma and likely a tail extending behind the object, propelled by the solar wind. Consequently, the primary prediction is straightforward. If the acceleration is indeed natural, telescopes should detect a considerable cloud of gas and dust surrounding the object. Spectroscopic analysis should confirm the presence of volatile compounds, such as water, carbon monoxide, carbon dioxide, or methane. The object would then exhibit behavior consistent with a comet, displaying all the characteristic signs of sublimation-driven activity. Conversely, if no discernible large cloud materializes, and if the mass loss is negligible or absent, the hypothesis of natural outgassing would be considerably weakened. This outcome would represent a significant scientific finding, implying that the acceleration originates from an unknown source that does not necessitate the expulsion of substantial material. In such a scenario, non-natural or technological explanations would gain greater plausibility. Key measurements to monitor include astrometric residuals, which represent the discrepancies between the object's actual observed position and its predicted position based purely on gravitational influences. These residuals are instrumental in quantifying the magnitude and direction of any non-gravitational forces. As more observational data is gathered in the coming weeks, astronomers will refine the object's orbit and achieve greater precision in quantifying the acceleration. Spectroscopy remains another crucial analytical technique. By dissecting the light emanating from the object into its constituent wavelengths, scientists can identify the specific molecules and atoms present. 3-Eye Atlas has already drawn attention for its unusual coloration, described as exhibiting a bluer hue than the Sun. This could indicate the presence of ionized carbon monoxide, a spectral signature associated with certain types of comets, or it may signify something entirely different. Detailed spectroscopic analysis will provide deeper insights into its composition and its compatibility with known cometary chemistry. Imaging also plays a vital role. The morphological characteristics of any observed coma or tail, the structure of any emitted jets, and the presence of asymmetries all offer valuable clues. Some reports have mentioned an anti-tail, a jet that appears to be directed towards the Sun rather than away from it. While unusual, this phenomenon is not unprecedented. Comets occasionally display features pointing forward due to observational geometry or rotational effects. High-resolution imagery will be essential to ascertain whether these observations are consistent with natural processes. Finally, radio astronomy offers another avenue of investigation. Claims circulating on social media suggest that the object emitted signals at 1.4 GHz, purportedly communications or course correction transmissions. These claims are entirely unverified, yet radio telescopes are nevertheless being employed to listen for such emissions. Should any unusual radio signals be detected, regardless of their frequency, they will be meticulously recorded and analyzed. While radio signals from comets are rare, they are not impossible, often being associated with plasma interactions. However, a strong structured signal would constitute a phenomenon of entirely different significance. The observational campaign faces inherent challenges. Timing and geometric considerations are particularly critical around perihelion. During this phase, the object was positioned in close proximity to the Sun in the sky, making observation difficult due to the overwhelming solar glare. As it now recedes from the Sun and approaches Earth, its visibility improves. However, by late December, following its close approach, it will begin to dim as it moves farther from both the Sun and Earth. This observation window is therefore quite narrow. A multitude of factors, including prevailing weather conditions, telescope availability, budgetary constraints, and the complexities of international coordination, all exert influence. Not every telescope can be utilized for observation every night. Subsequently, the acquired data must undergo processing, rigorous analysis, peer review, and formal publication. The scientific process inherently operates at a pace considerably slower than the rapid dissemination of information on social media. Claims may proliferate within hours, but observational confirmations or refutations typically require weeks or months of dedicated effort. Nevertheless, this is an exceptionally exciting period. We are witnessing a visitor from another star system in real time. The very same telescopes that probe distant exoplanets and analyze the atmospheric composition of alien worlds are now being directed towards an object traversing our immediate celestial neighborhood. This represents a rare confluence of opportunity and technological capability. By early 2026, definitive answers are expected. If 3I Atlas behaves as a typical comet, exhibiting substantial outgassing, a prominent coma, a discernible tail, and spectroscopic signatures of volatile compounds, then the natural explanation will prevail. The observed non-gravitational acceleration would be attributed to the comet's natural activity, perhaps amplified by its interstellar origin and composition. However, if the observational data reveals minimal mass loss, an absence of a significant coma, and yet the acceleration persists or displays a directional characteristic inconsistent with typical jetting, then a significant scientific anomaly will arise. This would not signify a catastrophic event, but rather a perplexing scientific puzzle that defies conventional models. At that juncture, the discourse will shift, and the more unconventional hypotheses, which we will explore next, will transition from mere speculation to subjects demanding serious scientific investigation. The subsequent phase of this inquiry will meticulously examine the debate between natural and non-natural explanations, the role of social media in amplifying unsubstantiated claims, and the profound implications should 3I Atlas prove to be something other than a comet. Part 6. Non-gravitational acceleration, natural explanations. Comets are often simplified as dirty snowballs, a description commonly used in introductory astronomy. The nucleus of a comet comprises a composite mixture of ice, rock, and organic compounds. As a comet approaches the Sun, solar radiation heats its surface, inducing sublimation, the direct transition of ices from a solid to a gaseous state, bypassing the liquid phase. The liberated gas carries dust particles along, forming a diffuse envelope known as a coma, and frequently a tail that trails away from the Sun. This outgassing process not only creates a visually striking phenomenon, but also generates a propulsive force. The momentum of the expelled gas molecules exerts a reactive force on the comet itself, analogous to a leaky balloon propelling itself through a room. While the magnitude of this effect is small, it is measurable and is referred to as a non-gravitational force, a phenomenon that astronomers have been detecting and modeling for decades. Therefore, when Avi reports a non-gravitational acceleration of 0.02 millimeters per second squared for 3I Atlas, the initial scientific assumption is that it is a consequence of outgassing. This represents the default hypothesis, the most scientifically parsimonious explanation. However, the specifics of the phenomenon are crucial. Loeb utilized a momentum conservation equation to estimate the requisite mass loss to account for this observed acceleration. The underlying formula is straightforward. The force exerted on the comet is equivalent to the rate of mass loss multiplied by the velocity of the outflowing gas. Since force is also equal to mass times acceleration, this equation can be rearranged to determine the mass loss rate. Assuming an outflow velocity of a few hundred meters per second, typical for cometary jets, and an acceleration of 0.02 millimeters per second squared, one can calculate the rate at which the comet is losing mass. The result is quite striking. If 3I Atlas possesses a mass of approximately 30 billion tons, The calculation indicates that it would need to shed roughly 5 billion tons per month to sustain this acceleration. This equates to approximately 1/6 of its total mass being lost within a 30-day period. Over several months, the comet would effectively evaporate a substantial portion of itself. Such a significant rate of mass loss should be readily observable. Astronomers would expect to witness a voluminous coma, a vast cloud of gas and dust enveloping the nucleus. The tail should be prominent, and spectroscopic analysis should reveal an abundance of volatile compounds. Yet, current observations suggest a more subtle phenomenon. Reports mention a jet directed towards the sun, and the object's coloration is anomalous, appearing bluer than anticipated. However, a colossal coma commensurate with this projected mass loss rate has not yet been definitively observed. This does not entirely invalidate the natural explanation. Comets exhibit variability. Their outgassing can occur episodically, influenced by rotational dynamics, the exposure of newly accessible ices, or the collapse of surface layers. It is plausible that the high mass loss rate was a transient event, a burst of activity near perihelion that has since subsided. Alternatively, the gas might be escaping through a concentrated jet rather than dispersing uniformly, rendering the coma less conspicuous from Earth. It is also conceivable that the composition of the expelled gas is such that it is transparent or carries minimal dust, thereby reducing its visibility. The bluer-than-solar hue is particularly intriguing. It could signify the presence of ionized carbon monoxide, a molecule that can dominate the spectral signature of certain cometary types. Carbon monoxide ice is more volatile than water ice, sublimating at lower temperatures and at greater distances from the Sun. An interstellar comet, having formed in a distinct stellar environment, might possess a different composition compared to comets originating within our solar system, potentially being richer in carbon monoxide or other exotic ices. Some imagery suggests the presence of what might be an anti-tail, a feature directed towards the Sun rather than away from it. This is an uncommon occurrence, but not entirely impossible. It can arise from the specific geometry of observation, where the observer's vantage point causes dust within the orbital plane to appear as if it were pointing forward. Alternatively, it could represent a genuine forward-directed jet driven by the object's rotation or localized heating. The natural explanation necessitates the coherence of all these elements: high mass loss, unusual composition, intermittent outgassing, and geometric effects. It presents a complex scenario, but comets are indeed complex entities, and their behavior is not uniform. An interstellar comet, having formed in a different stellar system under distinct conditions, could readily deviate from the patterns observed in solar system comets. The object's dimensions and mass also warrant consideration. Estimates suggest a diameter of at least several kilometers, possibly exceeding 5 kilometers, and a mass surpassing 30 billion tons. This qualifies as a substantial comet. To accelerate such an immense body through outgassing requires immense energy and a prodigious loss of material. It is comparable to attempting to propel a large cargo ship by jettisoning its cargo. While feasible, it necessitates the rapid expulsion of a considerable quantity of material. Analogies can be helpful here. Imagine a massive container vessel losing half of its cargo over a month to achieve a marginal increase in speed. This is plausible but would undoubtedly result in a dramatic spectacle, with containers visible strewn across the water, evidence of debris fields and material loss. Similarly, if 3I Atlas is losing 1/6 of its mass within a month, observable evidence, such as gas, dust, and a luminous envelope, should be present. What would constitute satisfactory evidence for the natural explanation? This would include the detection of a large coma consistent with the predicted mass loss rate. Spectroscopic confirmation of water, carbon monoxide, carbon dioxide, or other volatiles in the expected concentrations. Imaging that reveals a classic cometary structure, potentially including a tail and multiple jets. Most critically, the acceleration should exhibit a correlation with the object's distance from the Sun. As the solar heating diminishes, outgassing should decrease, and consequently, the acceleration should subside. If, however, the acceleration persists or even increases as the comet moves farther from the Sun, this would constitute a significant red flag. At present, the hypothesis of natural outgassing remains plausible but is under considerable strain. The requisite mass loss rate is exceptionally high, and the observational evidence remains ambiguous. The object's considerable size and mass further complicate the narrative. Nevertheless, comets have a history of surprising us. Oumuamua astonished us with its acceleration and elongated shape. Borisov, conversely, presented as entirely unremarkable. 3I Atlas might simply be the next surprise. A comet exhibiting extreme characteristics that push the boundaries of our current understanding of typical cometary behavior. Alternatively, it could be something entirely different. This possibility leads us to our next area of exploration, the exotic, technologically driven hypotheses that occupy the liminal space between speculation and established science. Part 7, Non-Gravitational Acceleration. Exotic technological hypotheses. What if the observed acceleration is not a natural phenomenon? What if 3I Atlas is not merely a comet exhibiting unusual behavior? What if it is an engineered construct, an object deliberately dispatched, a manufactured entity? Avi and his colleagues have published a research paper titled, "Is the Interstellar Object 3I Atlas Alien Technology?" This is not posed as a facetious question, but rather as a serious scientific inquiry framed within the parameters of what can be plausibly ruled out. The paper critically examines the possibility that the object is a technological artifact, potentially a probe dispatched by an extraterrestrial civilization. Several converging factors prompt this line of inquiry. Foremost is the non-gravitational acceleration. If this acceleration cannot be attributed to outgassing, or if the outgassing explanation strains credulity due to the immense mass loss required, then alternative mechanisms must be considered. Secondly, the estimates of the object's size and mass. A large, massive object experiencing a measurable acceleration implies a significant transfer of energy and momentum. Thirdly, its trajectory. Loeb has observed that the object's path through the inner solar system, its precise timing, and its alignment with Earth's orbital plane are statistically atypical. While not impossible, such a confluence of factors would be improbable for a random interstellar visitor. The energetic requirements are particularly noteworthy. For an object with a mass in the tens of billions of tons to sustain an acceleration of 0.02 millimeters per second squared over a period of weeks necessitates a substantial thrust. Applying the formula force equals mass times acceleration, and substituting values of 10 to the power of 13 kilograms for mass and 2 times 10 to the power of -5 meters per second squared for acceleration yields a force of approximately 200,000 newtons. This is equivalent to the sustained thrust of a moderately sized rocket engine. However, the efficiency of solar sails is significantly limited unless they are exceptionally large and highly reflective. Calculations suggest that a sail of sufficient size to accelerate this mass would need to span kilometers and be precisely oriented. Alternatively, a more exotic propulsion system, such as an ion drive, a fusion engine, or a technology yet to be conceived, might be employed. The social media reports concerning 1.4 GHz pings introduce another layer to this hypothesis. The frequency of 1.4 GHz holds particular significance in the search for extraterrestrial intelligence because it corresponds to the hydrogen line, a natural emission frequency from neutral hydrogen atoms. This frequency is sometimes referred to as the water hole in radio astronomy, representing a relatively quiet band in the electromagnetic spectrum where signals could propagate through space with minimal interference. If an advanced civilization were to transmit a signal, 1.4 GHz would represent a logical choice. However, a critical issue arises. There is no publicly verifiable detection of such pings originating from 3I Atlas. Radio telescopes continuously monitor the sky, and a strong, structured signal emanating from the object would undoubtedly have been detected. This claim remains unsubstantiated, residing within the realm of conjecture. Nevertheless, let us entertain the hypothesis. Assuming, for the sake of argument, that 3I Atlas is an artificial probe, what might its purpose be? Reconnaissance and observation are plausible objectives. It could have been drifting through interstellar space for millennia, a relic of a long-vanished civilization, continuing its programmed mission to survey star systems. Alternatively, it might be an active entity, deliberately altering its course to investigate objects of interest. Could it intentionally steer itself to intercept Earth? The concise answer is yes, provided it possesses the requisite capability. A probe equipped with a functional propulsion system could, in principle, modify its trajectory. However, the delta V required to transition from a 27 million kilometer miss to an actual intercept far exceeds 86 meters per second. Velocity changes on the order of kilometers per second, applied with precise timing and direction, would be necessary. This represents a considerable thrust sustained over an extended period. Loeb has also discussed the dark forest hypothesis in relation to 3I Atlas. The dark forest concept, popularized by science fiction author Liu Cixin, posits that the universe is teeming with civilizations, but they maintain silence to avoid detection by potentially hostile neighbors. Revealing one's presence could invite annihilation, thus compelling all entities to remain concealed within the cosmic dark forest. Loeb speculates that should 3 Atlas prove to be a probe, its actions might suggest a strategy of cautious observation from a distance, eschewing direct engagement. This notion, however, is purely hypothetical and involves a series of layered assumptions. The first assumption posits that the observed acceleration is not a natural phenomenon. The second assumption is that it is instead artificial. The third assumption asserts that an intelligent entity is controlling this artificial acceleration. The fourth assumption posits that this intelligence exhibits caution or specific intent regarding Earth. Each subsequent assumption diminishes the overall likelihood of this scenario. What might serve as definitive proof of a technological origin? Several indicators come to mind. Unforeseen radio transmissions, particularly those exhibiting structured patterns and containing informational content, would be significant. Another indicator would be sustained acceleration without a corresponding decrease in mass or expulsion of gas, a phenomenon known as non-volatile thrust signatures. Extremely minimal mass loss, coupled with high acceleration, would defy the principles of rocket propulsion unless an external energy source were involved. Highly reflective surfaces would suggest manufactured materials rather than natural geological formations. Alterations in attitude or orientation that cannot be attributed to uncontrolled tumbling would also be noteworthy. Should observations reveal any of these signs, the entire discourse would immediately shift. The extraordinary hypothesis would transition from fringe speculation to a plausible explanation demanding thorough investigation. Conversely, if none of these characteristic signatures emerge and the object continues to behave like an unusual but natural comet, then the technological hypothesis would recede into the background. The implications are profound. If the probe scenario is accurate, it would definitively establish that humanity is not alone in the universe. It would signify that another civilization has achieved a technological level capable of dispatching objects across interstellar distances. This would inevitably lead to inquiries about their motivations, their longevity, and their ultimate fate. Are they still active? Did they dispatch a solitary probe or a multitude? Is 3 Atlas an ancient artifact or a recent creation? Nevertheless, the magnitude of the stakes does not validate the hypothesis. Claims of an extraordinary nature necessitate extraordinary evidence. At present, the available evidence is, at best, ambiguous. The observed non-gravitational acceleration is a verified phenomenon, but its origin remains definitively unconfirmed as non-natural. The trajectory is indeed unusual, yet not entirely impossible for a random interstellar visitor. The reported radio signals lack verification. The absence of a significant coma is suggestive, but not conclusive. Scientific methodology is predicated on testing hypotheses, formulating predictions, and comparing them against empirical observations. The technological hypothesis also generates predictions. Specifically, the absence of a substantial gas cloud due to a lack of outgassing. Persistent acceleration as the object recedes from the Sun, indicative of a propulsion system not reliant on solar power. The potential for radio transmissions or other non-thermal signatures. Over the ensuing months, observational data will serve to test these predictions. Should the object be confirmed as natural, humanity will still have gained valuable knowledge. We will have extended the frontiers of cometary science, explored the chemical and dynamic properties of interstellar visitors, and rigorously tested our theoretical models against an extreme case. If, however, the object is determined to be artificial, that would constitute the most significant discovery in human history. Regardless of the outcome, the observations anticipated in late 2025 and early 2026 promise to be exceptionally compelling. Our attention now shifts to the dissemination of this narrative, specifically how social media platforms transformed scientific data into a story of alien interception and conspiracy. This leads us to Part 8. The social media narrative and conspiratorial framing. Posts began appearing on X in mid-October 2025. An independent researcher, unaffiliated with any major academic institution, presented a series of assertions. The central claim was straightforward: 3I Atlas is accelerating. If it maintains an acceleration of 0.02 millimeters per second squared for 50 days, it will attain a velocity change of 86 meters per second. This alteration in velocity, if applied with the correct vector at the opportune moment, could align the object with Earth on the 19th of December, 2025. Subsequently, the claims escalated. The researcher proposed that the acceleration was not random, but deliberate. The object, it was suggested, was actively maneuvering, correcting its course, and steering itself toward Earth. There were also mentions of 1.4 gigahertz pings detected in proximity to Mars, purported communications or signal exchanges between the object and an unspecified entity. The narrative thus evolved from an intriguing scientific anomaly to an imminent threat. An alien probe was targeting us. Let us deconstruct this assertion systematically. The data concerning the acceleration is indeed factual. Avi Loeb reported it, and it is derived from astrometric observations sourced from reputable institutions. The arithmetic, the calculation that 0.02 millimeters per second squared multiplied by 50 days equals 86 meters per second, is also accurate, representing fundamental physics with no inherent errors. However, the subsequent assumptions introduce uncertainty. The assumption that the acceleration will persist for precisely 50 days. The assumption that its directionality is toward Earth. The assumption that the timing perfectly coincides with Earth's orbital position. None of these propositions have been substantiated. They are extrapolations, speculative guesses based on limited data. The interpretation, the assertion that the object is aligning itself with Earth, is where empirical data ceases and narrative begins. Alignment implies intent. It suggests the object is deliberately navigating towards our planet. There is no corroborating evidence for this. The projected closest approach distance remains at 270 million kilometers. NASA has explicitly stated there is no threat. The geometrical configuration does not support an intercept scenario unless a confluence of multiple improbable factors occurs. The 1.4 gigahertz pings are unverified. No major observatory has confirmed any radio emissions emanating from 3 Atlas. Were such a signal to exist, radio astronomers would be intensely focused on it. The lack of confirmation does not definitively prove the pings did not occur, but it necessitates skepticism in their absence of evidence. So, how did this narrative gain such traction? Social media platforms inherently thrive on uncertainty and dramatic tension. A scientific anomaly, a gap in our current understanding, provides fertile ground for conjecture. Individuals take the raw data, overlay their own interpretations, and construct compelling narratives. These narratives propagate far more rapidly than the underlying scientific explanations because they are inherently more sensational. The notion of an alien probe targeting Earth is undeniably a more captivating headline than a comet exhibiting unusual outgassing. The psychological underpinnings of this phenomenon are fascinating. Humans possess an innate drive to identify patterns, often perceiving connections where none objectively exist. We are predisposed to narratives that lend meaning to perceived chaos. An interstellar object exhibiting unexplained acceleration is not merely a comet behaving erratically. It is interpreted as a sign, a message, perhaps even a warning. This interpretation resonates with broader cultural anxieties concerning the unknown, the vastness of the cosmos, and our preparedness for potential extraterrestrial contact. The amplification of these sentiments is further fueled by conspiratorial framing. Once the premise is established that the object might be artificial, every ambiguity is reinterpreted as corroborating evidence. The absence of a visible coma becomes proof it's not a comet. Its unusual coloration suggests engineered materials. Its trajectory is seen as deliberate targeting. The lack of official confirmation of radio pings is framed as an intentional cover-up. Consequently, the narrative becomes self-sustaining, resistant to factual contradiction. This phenomenon is not unique to 3 Atlas. Oumuamua, for instance, underwent a similar cycle. A peculiar object emerges, scientists acknowledge its enigmatic nature, and the Internet subsequently fills the void with extraterrestrial explanations. Occasionally, even scientists themselves, like Loeb, engage with these speculations. Loeb is recognized for publicly entertaining exotic hypotheses, advocating for the consideration of all possibilities, including technological origins. While such openness is beneficial for scientific inquiry, it also provides fodder for sensationalism. Mainstream media outlets frequently amplify these stories, often in simplified or exaggerated forms. Headlines may proclaim alien probe, even when the accompanying article offers a more nuanced perspective. The New York Post, for example, published an article quoting Loeb regarding 3I Atlas, framing it as a potential alien propulsion system. Such framing is critical, The majority of readers typically do not progress beyond the headline, absorbing the implication that scientists suspect alien involvement, and this impression becomes the prevailing story. The responsibility in scientific communication lies in clearly delineating between established data and speculative extrapolation. The data demonstrably indicate a non-gravitational acceleration and nothing more. The extrapolation to an Earth intercept, intentional maneuvering, and alien technology represents a series of interpretations layered upon the empirical findings. While these interpretations may prove accurate, they are not established facts. A delicate balance must be struck. On one hand, we should avoid prematurely dismissing possibilities. Scientific progress often stems from exploring seemingly improbable ideas. On the other hand, speculation should not be equated with evidence. The assertion that 3 Atlas is aligning with Earth does not carry the same weight as the observation that it exhibits non-gravitational acceleration. One is a measured quantity, the other an inference. Social media platforms tend to blur this distinction, rendering all pronouncements as claims, theories, or possibilities. This diminishes the signal-to-noise ratio, leading to arguments about potential threats without a consensus on the fundamental data. Misinformation proliferates not necessarily due to deliberate falsehoods, but because the boundary between data and interpretation becomes indistinct. This raises a meta-question. Are we adequately prepared for the potential ramifications? What if the object, while natural, is extraordinarily unusual, pushing the boundaries of cometary physics? What if it is indeed artificial, confirming our solitude is an illusion? How do we, as a society, navigate information in an environment where truth and speculation coexist seamlessly within the same digital feed? The social media discourse surrounding 3i Atlas serves as a pertinent case study illustrating the intersection of scientific inquiry and narrative construction. The subsequent section will explore what transpires if this narrative proves to be more than mere speculation, if the object demonstrably performs an unexpected action. This brings us to Part 9, Worst-Case Scenario Hypothesis, Intersect. Let us engage in a hypothetical exercise. This constitutes scenario analysis, not a prediction. What if all the preceding assumptions were accurate? What if 3 Atlas, through some means, managed to alter its trajectory sufficiently to intercept Earth? What would be the consequences of such an event? First, let us establish the parameters. Estimates for the size of 3i Atlas vary, ranging from a few hundred meters to several kilometers in diameter. Some calculations, based on its luminosity and assumed reflectivity, suggest a diameter of 5 kilometers or even greater. Mass estimates exceed 30 billion tons, potentially reaching higher figures. This represents a celestial body of immense proportions, hurtling through space. Interstellar objects traverse at considerable speeds. Upon entering a solar system on a hyperbolic trajectory, they are not gravitationally bound to the star, thus their velocity does not significantly diminish. 3i Atlas is currently traveling at approximately 60 kilometers per second, equivalent to 60,000 meters per second, or over 130,000 miles per hour. At such velocities, kinetic energy escalates dramatically. The formula for kinetic energy is straightforward. Energy equals 1/2 multiplied by mass multiplied by velocity squared. Employing a conservative estimate, let us assume a mass of 30 billion tons, which translates to 3 multiplied by 10 to the power of 13 kilograms. For velocity, we will use a mid-range estimate of 30,000 meters per second. Plugging these figures into the equation, 1/2 multiplied by 3 multiplied by 10 to the power of 13 multiplied by 9 multiplied by 10 to the power of 8 yields approximately 1.35 multiplied by 10 to the power of 22 joules. To contextualize this immense energy, consider that 1 megaton of TNT releases approximately 4.2 multiplied by 10 to the power of 15 joules. Dividing the kinetic energy by this value results in approximately 3.2 million megatons. For comparative purposes, the most powerful nuclear weapon ever detonated, the Soviet Tsar Bomba, had a yield of 50 megatons. Such an impact would therefore be 60,000 times more potent. The ramifications would be unequivocally catastrophic. An object of this magnitude and velocity would penetrate the atmosphere within mere seconds. It would not have sufficient time to decelerate or ablate significantly. It would impact the surface at nearly its full velocity, instantaneously releasing its colossal kinetic energy. The resulting explosion would dwarf any event in human history, whether natural or artificial. Firestorms would erupt across continental landmasses. The shockwave would obliterate everything within hundreds of kilometers of the impact site. Earthquakes of unprecedented magnitude would reverberate through the planet's crust. Should the impact occur in an ocean, colossal tsunamis, thousands of meters high, would race across ocean basins at speeds rivaling jet aircraft, devastating coastal regions. However, the immediate devastation would merely be the prelude. The immense energy released would vaporize the impactor and a vast quantity of terrestrial material, propelling it into the atmosphere. Dust and aerosols would rapidly disperse globally within days, obscuring sunlight. Global temperatures would plummet, halting photosynthesis and leading to widespread crop failure. The subsequent famine would claim more lives than the initial impact itself. This scenario constitutes an extinction-level event, not necessarily the complete annihilation of all life, as Earth has endured more severe cataclysms. However, it would undoubtedly lead to the extinction of most large animal species, including humans. We are contemplating a scenario comparable to the impact event that extinguished the dinosaurs approximately 66 million years ago. Now, let us consider a less extreme, though still significant, scenario. Suppose 3 Atlas does not impact Earth, but rather passes at a considerably closer proximity than the predicted 1.8 astronomical units. Imagine a flyby at tens of thousands of kilometers, approximately the distance to geostationary satellites. Such a close approach would still be profoundly dramatic. The object's gravitational influence could marginally perturb Earth's orbit, though likely imperceptibly due to Earth's vastly greater mass. However, potential electromagnetic and plasma interactions could prove noteworthy. If the object possesses a magnetic field or carries charged particles, phenomena such as enhanced auroras, radio disruptions, and even temporary satellite malfunctions could occur. Furthermore, there is the question of potential debris. If 3 Atlas is shedding material, either through outgassing or fragmentation, a close flyby could inject dust and particles into Earth's atmosphere, potentially intensifying meteor showers. Spacecraft operating in low Earth orbit would face increased risks from impacts. The International Space Station, numerous satellites, and all orbital assets would require vigilant monitoring. From a scientific perspective, a close flyby would represent an unparalleled opportunity. Telescopes would acquire data with unprecedented resolution. Radar imaging could map the object's surface in detail. Spectroscopic analysis could provide in-depth compositional information. If the object were indeed artificial, its nature would be undeniably evident at such close range. However, let us return to the fundamental question. What magnitude of velocity change, or delta V, would actually be required to transform the predicted miss into an intercept? The projected miss distance is 270 million kilometers. To bridge this gap, a substantial alteration in trajectory would be necessary. A delta V of 86 meters per second is demonstrably insufficient unless the geometrical alignment were extraordinarily fortuitous. Performing a rough estimation, the object's velocity is 60 kilometers per second. A 1% change in velocity, amounting to 600 meters per second, might shift the missed distance by several million kilometers, contingent upon the direction and timing of the maneuver. To effect a deviation of 270 million kilometers, a velocity change measured in several kilometers per second, applied consistently over weeks or months in a precisely determined direction, would likely be required. This is not achievable with an acceleration of 0.02 millimeters per second, squared sustained for merely 50 days. A considerably greater acceleration, maintained for an extended duration or applied much earlier in its trajectory, would be necessary. The numerical data do not support an intercept scenario based on the reported acceleration figures. Therefore, while the worst-case hypotheses are indeed terrifying, the chain of assumptions required to reach them is extensive and precarious. The object would necessitate a propulsion system capable of generating immense thrust. Maneuvering would have had to commence months or years prior, not solely near its perihelion. It would require precise knowledge of Earth's position and velocity. Even then, the energetic considerations are daunting. If the object were artificial and deliberately targeting Earth, what would be its intent? Observation appears to be the most plausible motive. Why expend the resources to dispatch a probe across interstellar space, only to obliterate both itself and its target in a collision? A flyby scenario seems far more logical, approaching closely enough to study the planet, its atmosphere, its biosphere, and potentially even its technological signatures before continuing its journey. Alternatively, it is possible that the object is not targeting Earth at all. The trajectory might be coincidental, a consequence of dynamical forces within its originating star system. We may be projecting intent onto randomness, perceiving patterns where none exist. What monitoring and defense capabilities do we currently possess? At present, they are limited. Planetary defense systems, such as NASA's Double Asteroid Redirection Test, DART, are designed for smaller, slower-moving objects detected years in advance. An interstellar intruder traveling at 60 kilometers per second, detected only months before its closest approach, lies beyond our current deflection capabilities. Early warning networks are crucial. If such an object were detected years prior, we might have sufficient time to formulate a response mission, possibly even intercepting it for study. However, 3 Atlas was detected in July 2025, a mere few months before its perihelion and approach to Earth. This time frame is insufficient for the implementation of a deflection mission. Consequently, while the worst-case scenarios underscore the importance of preparedness, they do not accurately reflect our present circumstances. The established reality, based on all credible orbital calculations, is that 3 Thud Atlas poses no threat. The missed distance is comfortably substantial, and its trajectory is well understood. While various agencies are monitoring the object, there are no indications of alarm. Moving forward, we will broaden our perspective to examine the wider implications of interstellar objects for planetary defense and the scientific exploration of extrasolar systems. This leads us to Part 10, Broader Implications for Interstellar Objects, Planetary Defense. 3I Atlas represents only the 3rd confirmed interstellar object ever detected. The initial discovery was Oumuamua in October 2017. The second was Borisov, identified in August 2019. Prior to these discoveries, direct evidence of objects originating from other star systems visiting ours was non-existent. Now, we possess conclusive proof that they do, and likely with greater frequency than previously estimated. The study of interstellar objects offers a unique vantage point from which to examine the universe beyond our solar system. These are fragments of alien worlds, debris from planetary systems situated light years away, delivered directly to our cosmic doorstep. By meticulously analyzing their composition, structure, and behavior, we can glean invaluable insights into the chemistry and dynamics of star systems that remain otherwise inaccessible to us. Oumuamua presented an enigma from its inception. Its elongated shape, erratic rotational pattern, and subtle non-gravitational acceleration ignited extensive debate. Was it a comet, an asteroid, or something entirely different? Spectroscopic analysis revealed no discernible coma or tail, nor any overt signs of outgassing. Nevertheless, it exhibited acceleration as it moved away from the Sun, implying a force beyond gravitational influence. Loeb famously proposed the speculative possibility of a light sail, a thin, reflective sheet propelled by solar radiation. The majority of astronomers, however, favored the interpretation that it was a comet exhibiting unusual characteristics, perhaps composed of hydrogen ice or nitrogen ice that sublimated without forming a visible cloud. Borisov, in contrast, presented a more conventional profile. It closely resembled a typical comet, complete with a coma, a tail, and spectroscopic signatures indicative of water and carbon monoxide. Its behavior was entirely consistent with that of an icy body approaching the Sun. In many respects, Borisov proved reassuring, demonstrating that not every interstellar object deviates from expected norms. Some are simply comets originating from distant locales. 3 Atlas occupies an intermediate position between these two extremes. It exhibits certain cometary characteristics, alongside anomalies that defy simple categorization within established models. Its non-gravitational acceleration is more pronounced than anticipated for its size. If attributed to outgassing, its mass loss rate appears extreme. Its coloration and the potential presence of an anti-tail introduce further peculiarities. What does this collective evidence suggest about interstellar objects generally? It indicates their inherent diversity, cautioning against the assumption that they all conform to the behavior patterns of solar system comets or asteroids. It implies that their composition, structure, and evolutionary history are intrinsically linked to their place and method of formation. The dynamics of interstellar objects also pose challenges to our current understanding. How frequently do they traverse our solar system? From whence do they originate? Are they ejected from planetary systems due to gravitational interactions with massive planets? Or are they remnants of stellar formation, material that failed to coalesce into planets? Detection rates suggest that interstellar objects pass through the inner solar system with greater frequency than we had previously hypothesized. With the advent of more advanced telescopes and comprehensive sky surveys, our ability to detect them is steadily improving. 3 Atlas was initially identified by the same system dedicated to locating near-Earth asteroids. Future observational initiatives, such as the Vera C. Rubin Observatory, are projected to detect a significantly greater number of these objects. Within the next decade, it is plausible that we will be identifying 1 or 2 such objects annually. This ongoing discovery process has direct implications for planetary defense. While 3I Atlas currently poses no immediate threat, the demonstrable reality of extrasolar bodies traversing our solar system implies that future visitors could approach much closer. Consequently, our capabilities for detection and response must be enhanced. Planetary defense against interstellar objects presents a more formidable challenge than confronting objects originating within our solar system for several critical reasons. Firstly, their velocity. Interstellar objects travel at significantly higher speeds, measured in tens of kilometers per second, in contrast to the mere few kilometers per second characteristic of solar system objects. The diminished reaction window and heightened difficulty in deflection are significant concerns. Secondly, unpredictability reigns supreme. Their orbital paths remain a mystery until their arrival. Unlike celestial bodies within our solar system, which adhere to discernible trajectories we can monitor for years, interstellar visitors materialize without warning. Thirdly, our observational opportunities are fleeting. They traverse our vicinity rapidly, vanishing from our sight. We may have mere months for comprehensive study. Consequently, mission planning assumes paramount importance. Should we detect a noteworthy interstellar entity years in advance of its closest approach, could a spacecraft be dispatched for an interception? The answer is contingent upon the trajectory and our preparedness, a decidedly tentative maybe. Initiatives, such as the European Space Agency's Comet Interceptor, are specifically engineered for swift responses to transient celestial phenomena. Expanding the fleet of such missions, strategically positioned in space and poised for immediate deployment upon target detection, could fundamentally alter our capacity to investigate interstellar voyagers. Enhanced radar and optical tracking systems would also prove invaluable. Superior astrometry translates to more precise orbital calculations, facilitating earlier identification of potential hazards and more accurate characterization of intriguing objects. Artificial intelligence offers a crucial aid in sifting through immense datasets, flagging anomalies, and predicting trajectories. Furthermore, technological advancements stem from this research. Simulating the dynamics of high-velocity objects deepens our comprehension of impact physics, yielding applications in material science and planetary geology. Tracking faint, swift-moving entities pushes the boundaries of instrumentation and data processing capabilities. These advancements benefit not only planetary defense, but also the broader field of astronomy. Now, let us consider the ramifications should 3I Atlas prove to be artificial. The impact on the pursuit of extraterrestrial intelligence would be nothing short of monumental. For decades, SETI has diligently monitored radio frequencies, seeking deliberate transmissions from other civilizations. However, an interstellar probe, a physical artifact dispatched across the cosmos, signifies an entirely different paradigm of communication and exploration. It suggests a civilization capable of constructing sophisticated machinery, launching it into space, and either persisting to this day or leaving behind these enduring relics. Even if 3I Atlas is a naturally occurring but peculiar object, its implications for solar system formation and extraterrestrial chemistry remain profound. It indicates a greater diversity in the physics governing small celestial bodies than previously understood. Our models of comets, asteroids, and planetesimals would necessitate revisions to encompass a wider array of compositions and behaviors. In either scenario, 3I Atlas serves as a compelling wake-up call. Regardless of whether its ultimate designation is a confirmed comet or a groundbreaking discovery, the object underscores the interconnectedness of our solar system with the wider cosmos. The galaxy is a boundless expanse, teeming with innumerable stars and planets, and the void between them is far from empty. Objects traverse, collide, escape, and drift. Some of these celestial wanderers find their way to our doorstep. The public's fascination with alien probes can galvanize attention and secure funding for space science, yet it also carries the risk of misinterpretation. Planetary defense organizations must meticulously manage both the data and the narrative, disseminating accurate information while acknowledging inherent uncertainties. The boundary between responsible conjecture and sensationalism is perilously thin. Scientists such as Avi Loeb navigate this delicate balance with deliberate intent, advocating for an open-minded consideration of all possibilities. Critics, conversely, argue that entertaining extraordinary hypotheses without robust evidence erodes public confidence in scientific endeavors. This ongoing debate, however, is vital. It reflects the inherent tension between caution and curiosity, between conservatism and imagination. 3I Atlas, irrespective of its final classification, embodies this very tension. We now transition to recent significant advancements in other domains of space science that bear relevance to this narrative. Part 11. Recent breakthroughs in exoplanet atmosphere imaging. The year 2025 has been exceptionally fruitful for exoplanet research. The James Webb Space Telescope, commissioned in late 2021, has dedicated years to fine-tuning its instruments and observing distant worlds. This year, it achieved a remarkable feat: the capture of detailed molecular signatures within the atmosphere of a Neptune-sized exoplanet orbiting a star 60 light-years distant. The planet, identified as K2-18b, had been previously studied, but the infrared capabilities of JWST allowed astronomers to probe its atmosphere with unprecedented depth. The resulting spectrum revealed the presence of water vapor, methane, carbon dioxide, and tantalizing hints of dimethyl sulfide, a molecule on Earth primarily associated with biological processes. This detection remains tentative, requiring further observations for definitive confirmation. However, if substantiated, it represents the first potential biosignature identified in an exoplanet atmosphere. The significance for 3I Atlas lies in the applicability of these same analytical techniques to the study of cometary comas and jets. Spectroscopy, the process of separating light into its constituent wavelengths, elucidates the molecular composition of celestial bodies. Whether examining a planet 40 parsecs away or a comet 2 astronomical units distant, the fundamental method remains consistent. We inhabit an era where we possess the capacity to scrutinize the atmospheres of distant worlds and dissect the chemistry of interstellar visitors. The tools employed are remarkably similar. Instruments designed to observe exoplanets during transits, when they pass before their host stars, can also be repurposed to analyze the coma, jets, and any gaseous emissions from 3I Atlas. The exoplanet findings from 2025 powerfully illustrate the capabilities of contemporary astrochemistry. Decades ago, the detection of exoplanets was a monumental challenge, let alone the characterization of their atmospheres. Today, we are identifying individual molecules, assessing habitability, and actively searching for indications of life. This same technological prowess extends to nearer celestial phenomena. 3I Atlas may offer a tangible sample of extrasolar material, providing a direct probe into the chemical processes occurring in another star system. Its unusual characteristics, the anomalous acceleration, its peculiar coloration, and the observed anti-tail, render it a particularly intriguing subject. Should its composition prove to be unconventional, rich in molecules not typically found in solar system comets, it would offer invaluable insights into the diversity of planetary formation processes across the galaxy. The interdisciplinary nature of this scientific endeavor is striking. Planetary science, astronomy, instrumentation, chemistry, and physics converge seamlessly. Scientists engaged in the analysis of exoplanet spectra may collaborate with those studying 3I Atlas. The same telescopes can serve dual purposes. Consider a specific case study: the identification of water vapor and methane in K2-18b's atmosphere involved multiple observations during its transits across its host star. Each transit yielded a spectrum, revealing which wavelengths of light were absorbed by the planet's atmosphere. By comparing these spectra, astronomers discerned absorption lines corresponding to specific molecules. The precision demanded is extraordinary. We are speaking of detecting molecular concentrations in the parts per million range in atmospheres situated hundreds of trillions of kilometers away. Could analogous techniques uncover evidence of artificiality in 3I Atlas? It is a distinct possibility. If the object possesses a metallic surface, incorporates engineered materials, or exhibits unusual reflectivity, spectroscopic analysis might reveal such properties. Metals possess distinct spectral signatures. A surface composed of aluminum or steel would interact with light differently than rock and ice. Polymers, ceramics, and other manufactured substances all leave discernible fingerprints in spectral data. If 3I Atlas were indeed a probe or spacecraft, its surface materials could potentially indicate its origin. Natural objects are typically composed of silicates, organic compounds, and ices. Artificial constructs, however, might incorporate alloys, composites, and coatings designed for resilience in the harsh environment of space. Such distinctions should be detectable, provided high-resolution spectral data is obtained. The very telescopes employed to scrutinize distant worlds are instrumental in examining closer interstellar intruders. JWST, Hubble, and ground-based observatories equipped with adaptive optics all contribute to this effort. The synergistic relationship between exoplanet science and solar system astronomy represents one of the often underappreciated facets of modern astronomical research. A profound philosophical connection also exists. The study of exoplanets is fundamentally about understanding our cosmic context and discovering other worlds that might harbor life. The investigation of interstellar objects, in turn, involves encountering fragments of those worlds and receiving visitors from systems we may never physically reach. Both pursuits are driven by the same fundamental question: are we alone? If 3I Atlas is a natural phenomenon, it still acts as a messenger from another star, carrying information about its place of origin. If it is artificial, the implications are self-evident. In either case, it connects to the broader quest for life and intelligence beyond Earth. Coming up, we will delve into recent discoveries concerning dark matter and modified gravity theories, which may shed light on how we interpret anomalous accelerations observed in small bodies such as 3I Atlas. Part 12. New discoveries in dark matter or modified gravity. Earlier this year, astronomers unveiled findings from the Vera C. Rubin Observatory, which commenced operations in 2024. This observatory conducts the legacy survey of space and time, systematically imaging the entire southern sky at regular intervals. A primary objective of this survey is to map the distribution of dark matter by observing galactic clustering patterns and the bending of light around massive cosmic structures. Recent data has revealed discrepancies in galactic rotation curves that do not entirely align with prevailing dark matter models. Galactic rotation curves depict the orbital speeds of stars at various distances from a galaxy's center. In a galaxy comprising only visible matter, stars further from the center would orbit at slower speeds in accordance with Kepler's laws. However, observations indicate that these stars maintain orbital speeds comparable to those closer to the galactic core, suggesting the presence of unseen mass. This invisible mass is termed dark matter. The new data from the Rubin Observatory indicates that the distribution of dark matter within certain galaxies is more clumpy or diffuse than theoretical models had predicted. This could imply that our understanding of dark matter is incomplete, or it might hint at the validity of modified gravity theories. alternative frameworks to general relativity that account for galactic dynamics without recourse to unseen matter. The implications are far-reaching. Dark matter is theorized to constitute approximately 85% of all matter in the universe, yet it has never been directly observed. Its existence is inferred from its gravitational influence, manifesting in the rotation of galaxies, the bending of light around galaxy clusters, and the large-scale structure of the cosmic microwave background radiation. However, its fundamental composition remains unknown. Decades of experiments aimed at detecting dark matter particles, specifically weakly interacting massive particles, WIMPs, have yielded no definitive results. Detectors, situated deep underground and shielded from cosmic rays, await the rare collision of a dark matter particle with an atomic nucleus. To date, no conclusive evidence has emerged. The data from the Rubin Observatory introduces another layer of uncertainty. If the distribution of dark matter deviates from our established models, it raises questions about fundamental aspects of its behavior. Alternatively, a more radical possibility suggests that dark matter may not exist at all, and that gravity itself operates differently on cosmic scales than currently understood. Modified gravity theories, such as modified Newtonian dynamics, (MOND), propose that Newtonian laws become inadequate when gravitational acceleration drops to extremely low levels, as observed in the outer regions of galaxies. Instead of postulating unseen matter, these theories propose adjustments to the equations of motion. While MOND has demonstrated some success in explaining galactic rotation curves without invoking dark matter, it struggles to account for other observational phenomena, such as gravitational lensing and the cosmic microwave background. The debate between dark matter proponents and advocates of modified gravity has persisted for decades. The majority of physicists favor the dark matter hypothesis due to its ability to reconcile a broader range of observations and its better integration with our understanding of particle physics and cosmology. Nevertheless, the persistent lack of direct detection continues to sustain interest in modified gravity theories. How does this relate to 3I Atlas? When we observe a non-gravitational acceleration in an object like 3I Atlas, we operate under the assumption that our model of gravity is accurate. We calculate the object's predicted position based on the gravitational influence of the Sun, planets, and relativistic effects. Any deviation from this prediction is then classified as non-gravitational, implying it stems from a source other than gravity. But what if our gravitational model is subtly flawed? What if there are minor corrections, unaccounted forces, or subtle effects that have yet to be discovered? In such a scenario, what we currently interpret as thrust or outgassing might actually be a consequence of a misunderstanding of the fundamental physics at play. While this is a long shot, it warrants consideration. Historically, anomalies in orbital mechanics have been catalysts for new physics. The precession of Mercury's orbit, the gradual shift in its elliptical path, could not be explained by Newtonian gravity. Einstein's theory of general relativity provided a solution, demonstrating that the curvature of spacetime near the Sun was responsible for this phenomenon. Could the anomalies observed in the trajectories of small bodies be indicative of a similar breakthrough? It is improbable. The scales involved are vastly different. Dark matter and modified gravity theories are primarily concerned with galactic scales, where gravitational fields are weak and distances are immense. The inner solar system, through which 3I Atlas is traversing, features strong gravitational fields dominated by the Sun. Any deviations predicted by modified gravity theories would be negligible, far smaller than the observed acceleration. To provide perspective, the gravitational acceleration at Earth's distance from the Sun is approximately 6 millimeters per second squared. At 3I Atlas's perihelion distance of roughly 1.4 astronomical units, this acceleration is even greater. Modified gravity theories predict deviations from Newtonian gravity only when accelerations fall below approximately 10 to the power of -10 meters per second squared, 100 million times weaker than what 3I Atlas is experiencing. Therefore, any effect attributable to modified gravity would be utterly insignificant in this context. Nevertheless, the recent discoveries in dark matter research serve as a potent reminder that our comprehension of gravity and mass remains incomplete. We are still uncertain about the nature of dark matter. Direct detection of a dark matter particle has eluded us. Its existence is inferred from gravitational effects, yet its fundamental properties are unknown. This enigma intensifies when considering the cosmic scale. The accelerating expansion of the universe is attributed to an unknown entity termed dark energy. Similar to dark matter, its identity is a mystery. It accounts for approximately 68% of the universe's energy density, yet it is entirely invisible and detectable solely through its gravitational influence. Consequently, roughly 95% of the universe, comprising dark matter and dark energy, consists of entities we do not understand. If our models of mass distribution are incomplete, could we be misinterpreting the accelerations caused by small forces? Could factors such as radiation pressure, drag from the interplanetary medium, or interactions with the solar wind be more significant than we currently estimate? These are natural forces that do not necessitate exotic physics, but their magnitude might be underestimated. Sunlight exerts a pressure on objects in space. While this effect is minuscule for large, massive bodies, it can become significant for small particles or objects with a large surface area relative to their mass. Astronomers account for this phenomenon when calculating orbits, but these calculations depend on accurate knowledge of the object's size, shape, and reflectivity. Any uncertainties in these parameters could lead to inaccuracies in radiation pressure estimations. The Yarkovsky effect presents another subtle force. When a rotating object absorbs sunlight, it heats up. The warmed side then re-emits this energy as infrared radiation, generating a minuscule propulsive force. Over time, this can measurably alter an object's orbit. Asteroids, for instance, exhibit a slow inward or outward drift over millions of years due to the Yarkovsky effect. Again, astronomers model this phenomenon, but it requires detailed knowledge of the object's thermal properties, rotational rate, and surface composition. Drag from the interplanetary medium represents an even more subtle influence. Space is not an absolute vacuum. It contains a tenuous plasma of charged particles streaming outward from the sun. Objects moving through this medium, known as the solar wind, experience a minute drag force. For most objects, this effect is negligible. However, for an object as substantial and swift as 3I Atlas, could it have a discernible impact? The observed acceleration of 3I Atlas, measuring 0.02 millimeters per second squared, is exceedingly small. It hovers at the very edge of what can be reliably measured. Subtle systematic errors in astrometry, minor inaccuracies in modeling planetary perturbations, or unaccounted for forces could mimic the appearance of a non-gravitational acceleration. Astrometry, the precise measurement of an object's position in the sky, is an inherently challenging endeavor. It involves tracking a faint point of light against the backdrop of stars, aiming to pinpoint its location with fractions of an arcsecond accuracy. Atmospheric turbulence distorts the images, while telescope imperfections introduce optical aberrations. Temporal uncertainties add further noise to the measurements. Even with the most advanced instruments, a degree of measurement error is unavoidable. When fitting an orbital model to astrometric data, a complex equation is solved, balancing the gravitational forces exerted by the Sun and planets, and occasionally by larger asteroids. If the measurements contain subtle systematic biases, if timestamps are slightly inaccurate, or if the star catalog used to define positional references has errors, the resultant fitted orbit will exhibit residuals. These residuals, in turn, could be misinterpreted as a non-gravitational acceleration when they are, in fact, merely noise. That said, astronomers exercise considerable caution. They meticulously account for known forces. They model solar radiation pressure and the Yarkovsky effect, where absorbed sunlight generates a minor thrust. They also factor in planetary gravity and relativistic effects. If they report a residual acceleration, it signifies that these known factors are insufficient to explain the observation. The Jet Propulsion Laboratory and the Atacama Large Millimeter Array are world-class facilities responsible for the astrometric data cited by Avi Loeb. Their measurements are considered highly reliable. The 4 arc-second discrepancy mentioned by Loeb is significant and well above the instrument's noise floor, suggesting the non-gravitational acceleration is likely a genuine phenomenon rather than an artifact of flawed data. However, the interpretation of this acceleration, its precise cause, remains an open question. Outgassing is the default explanation. Yet, as previously discussed, this hypothesis necessitates a high rate of mass loss that has not been definitively observed. Could there be another natural mechanism that we are currently overlooking? One potential explanation is fragmentation. If 3I Atlas is undergoing breakup, shedding material as it heats up, the ejected fragments carry momentum. The resulting reaction force would accelerate the main body. This is analogous to outgassing but driven by mechanical disintegration rather than sublimation. Comets occasionally fragment, particularly when subjected to tidal forces or rapid rotation. If 3I Atlas is a rubble pile, a loosely aggregated collection of rocks and ice held together primarily by gravity, it might be inherently unstable. Another speculative possibility involves electrostatic effects. Objects in space can accumulate electric charge through interactions with the solar wind and cosmic rays. If the charge distribution within the object is asymmetric, its interaction with the interplanetary magnetic field could generate small forces. While this effect would be minute, it represents a natural mechanism that does not rely on outgassing or artificial propulsion. The connection between 3I Atlas and dark matter is speculative, primarily serving as a narrative hook to engage viewers with the boundary between established and unknown physics. Could an interstellar object harness some form of propulsion or react to an as-yet undiscovered ambient medium? If our models of gravity and mass are incomplete, might non-gravitational acceleration signify something other than what we currently understand? Imagine the possibility of a fifth fundamental force beyond gravity, electromagnetism, and the strong and weak nuclear forces. Physicists have been actively searching for such fifth forces for decades, conducting highly precise experiments to ascertain whether gravity behaves precisely as predicted by general relativity. To date, no definitive deviations have been confirmed, yet the prospect remains tantalizing, particularly in unexplored scales or regimes. An interstellar object like 3I Atlas, originating from a vastly different cosmic environment, might interact with forces or fields unfamiliar to objects within our solar system. Its composition, forged in another star system under distinct conditions, could incorporate elements or structures that respond to the interplanetary medium in unforeseen ways. These are provocative questions, but they should not overshadow more conventional explanations. Outgassing remains the leading hypothesis. The object is most likely a comet possessing unusual characteristics rather than a manifestation of entirely new physics. The elegance of scientific inquiry lies in its reliance on empirical evidence rather than conjecture. Observations serve as the ultimate arbiters. Should the celestial body designated 3I Atlas exhibit all the characteristics of a comet, such as substantial outgassing, the presence of a coma, and spectroscopic indicators of volatile compounds, then its observed acceleration becomes readily explicable. Conversely, if these anomalies persist without a discernible natural cause, it compels us to consider more unconventional explanations. The link to phenomena like dark matter or modified gravitational theories at this juncture is more a philosophical contemplation than a practical certainty. It serves as a potent reminder that our current comprehension of the cosmos remains incomplete, a testament to humanity's ongoing pursuit of knowledge and refinement of theoretical frameworks. Irrespective of its ultimate classification, 3I Atlas represents a crucial data point within this continuous scientific endeavor. Our next exploration delves into the transformative role of artificial intelligence in celestial orbit prediction and anomaly detection, potentially illuminating the true nature of 3I Atlas. This segment, designated as Part 13, focuses on AI-driven astrometric orbit prediction tools. Artificial intelligence is revolutionizing our methods of cosmic study. Machine learning algorithms possess the remarkable ability to process immense volumes of data, discern intricate patterns, flag deviations, and generate predictions with superior speed and accuracy compared to conventional approaches. In the year 2025, the scientific community witnessed the release of several novel AI-powered tools for astrometry and orbit prediction, and their impact has already become significant. One such innovation is OrbNet, a sophisticated neural network developed through a collaborative effort involving multiple universities and space agencies. OrbNet processes astrometric data, essentially recorded observations of an object's positional changes over time, and compares them against a purely gravitational theoretical model. It then quantifies the differences, known as residuals, between observed and predicted positions, flagging any objects exhibiting substantial discrepancies. OrbNet underwent extensive training on decades of data pertaining to asteroids and comets, thereby acquiring a nuanced understanding of what constitutes typical celestial behavior and what deviates from it. When encountering an object like 3I Atlas, which displays measurable non-gravitational acceleration, OrbNet does not merely flag it. It proposes potential underlying causes based on patterns it has previously identified. These potential causes include outgassing, fragmentation events, collisions, the effects of radiation pressure, and even hypothetical unknown propulsion systems. The significance of this capability cannot be overstated. Subtle orbital deviations that might be overlooked or inadequately modeled by classical methods can be readily identified by AI. Human astronomers, when fitting orbits to observational data, might dismiss minor residuals as mere noise. AI, however, with its capacity to simultaneously analyze thousands of parameters, can detect subtle patterns that elude human perception. In the case of 3I Atlas, AI systems are instrumental in refining its orbital trajectory, detecting minute thrust vectors, and either substantiating or refuting hypotheses regarding potential maneuvers. If the object's acceleration exhibits temporal variability, fluctuates with its distance from the Sun, or displays directional inconsistencies with known outgassing phenomena, AI will be the first to identify these characteristics. Another significant tool, Astro AI, was introduced by the European Space Agency this year. This system employs reinforcement learning to forecast the future positions of near-Earth objects and interstellar visitors. Through training on historical data and simulating millions of potential trajectories, it can accurately estimate the corrective velocity changes required to achieve specific objectives, such as aligning with a designated target. Researchers have already leveraged Astro AI to analyze 3I Atlas. They inputted the observed acceleration, its current orbital parameters, and Earth's position. The AI then executed simulations posing the question, what change in velocity, applied at what specific time and in which direction, would result in an Earth intercept on December 19th? The outcome was unequivocal. The required velocity modification, or delta V, is considerably greater than 86 meters per second. Achieving such an intercept would necessitate several kilometers per second of applied velocity change, initiated months in advance with extremely precise directional control. The claims circulating on social media simply do not withstand rigorous modeling. This is precisely where AI excels. It can systematically explore vast parameter spaces, evaluating thousands of scenarios within mere seconds. In contrast, a human astronomer might manually compute only one or two scenarios. AI, however, computes all plausible scenarios and identifies those that are physically tenable. Nevertheless, AI is not without its limitations. Its efficacy is directly proportional to the quality of its input data. If the astrometric observations contain systematic errors, or if the object's motion exhibits complexity beyond the assumed model, AI may generate misleading conclusions. It could incorrectly flag anomalies that are not real, or fail to detect subtle effects that were not included in its training dataset. Furthermore, AI can identify correlations but not always establish causation. It might observe a correlation between acceleration and solar distance, suggesting outgassing, but it cannot definitively determine the specific chemical processes responsible. Such determinations require supplementary data from spectroscopy, imaging, and expert human interpretation. Consequently, the role of AI in the investigation of 3I Atlas is supportive rather than conclusive. It assists in refining orbital predictions, identifying patterns, and discarding improbable scenarios. Ultimately, the definitive judgment regarding the object's origin, whether natural or artificial, a comet or a probe, rests upon observational evidence and sound scientific reasoning. An additional dimension of AI's application in astronomy warrants mention: pattern recognition in radio signals. The ongoing search for extraterrestrial intelligence generates an enormous volume of data. Radio telescopes meticulously scan the heavens, capturing signals across millions of distinct frequency channels. The vast majority of these detected signals are either background noise, terrestrial interference, or naturally occurring astrophysical phenomena. The prospect of identifying a genuine techno-signature, an artificial signal originating from another civilization, is akin to locating a singular grain of sand on a cosmic beach. AI plays a crucial role in this endeavor. Algorithms, specifically trained to recognize patterns within noise, can flag candidate signals for human scrutiny. They can effectively filter out terrestrial interference, identify frequency drifts indicative of a transmitter situated on an orbiting or moving platform, and detect modulation patterns that suggest the presence of encoded information. Should 3I Atlas be emitting radio signals, as the social media posts allege with claims of 1.4 gigahertz pings, AI would almost certainly detect them. The absence of any reports from major observatories, despite continuous sky monitoring, serves as compelling evidence against the existence of such signals. AI is designed to be highly effective in detecting such phenomena. If a structured radio emission were emanating from the object's direction, it would have been flagged, rigorously analyzed, and either confirmed or attributed to interference. Therefore, AI-driven orbital analysis predicts that by late 2025 and early 2026, we will possess definitive updates regarding 3I Atlas's trajectory. Orbital residuals will be quantified with exceptional precision. Any persistent accelerations will be mapped in 3 dimensions, and temporal correlations with solar distance, object rotation, or other relevant factors will be identified. Consequently, the hypothesis of a directed maneuver towards Earth will be either confirmed or conclusively refuted. The inherent transparency of AI tools also contributes significantly to public trust. The results generated by these systems are reproducible, verifiable, and can be independently scrutinized by researchers worldwide. Unlike proprietary models or opaque calculations, open-source AI platforms empower anyone with access to the relevant data to conduct their own analyses. This process democratizes scientific discovery, making it considerably more challenging for misinformation to gain traction. Moving forward, we will examine advancements in radio astronomy, with a particular focus on the 1.44 GHz band and its implications for detecting potential technosignatures from objects like 3I Atlas. This is Part 14, Advances in Deep Space Radio Astronomy, 1.4 GHz and beyond. The field of radio astronomy has experienced a remarkable year. In early 2025, the Breakthrough Listen project, a prominent initiative dedicated to the search for technosignatures, released findings from a comprehensive survey encompassing millions of stars across the 1.2 to 1.8 GHz frequency range. This spectrum includes the 1.4 GHz hydrogen line, a natural frequency considered a prime candidate for interstellar communication. The survey yielded no confirmed technosignatures, but established stringent observational constraints. It implies that if advanced civilizations were broadcasting powerful radio signals at 1.4 GHz within a few thousand light-years of Earth, such signals would have been detected. The pervasive silence is, in itself, informative. It suggests that either intelligent civilizations are exceedingly rare, they do not communicate in this specific frequency band, their signals are too weak for our current detection capabilities, or they are deliberately maintaining a low profile. Progress in signal processing techniques, the deployment of larger antenna arrays, and AI-driven filtering have collectively enhanced the sensitivity of radio astronomy to unprecedented levels. Facilities such as the Meerkat Array in South Africa, the Very Large Array in New Mexico, and the soon-to-be-completed Square Kilometer Array are poised to push observational sensitivity even further. We are entering an era where the detection of faint radio emissions from nearby stars or passing celestial objects is not only feasible, but becoming a routine occurrence. This brings us to the social media assertion concerning 1.4 GHz pings purportedly originating from 3I Atlas. The claim posits that the object emitted structured signals in the vicinity of Mars, possibly as communication for course correction or as a form of greeting. The chosen frequency of 1.4 GHz is highly significant. It resides within the water hole, a relatively quiet segment of the radio spectrum characterized by minimal galactic background noise and efficient signal propagation. If an advanced civilization were to transmit a signal intended for detection by others, 1.4 GHz would represent a logical choice due to its universal nature. The hydrogen line is a fundamental constant recognized throughout the universe, and any civilization possessing radio astronomy capabilities would likely understand its significance. However, the critical issue is the complete absence of any publicly available peer-reviewed detection of such signals emanating from 3I Atlas. Radio telescopes continuously monitor the sky. Projects like Breakthrough Listen specifically target transient signals, bursts, and anomalies. Had 3I Atlas been emitting 1.4 gigahertz pings of sufficient strength to be detectable from Earth or even near Mars, it is highly probable that they would have been observed. Is it possible that the signals were too weak? This is a plausible scenario. Radio signals attenuate with distance according to the inverse square law. At a distance of 1 or 2 astronomical units, a low-power transmitter might fall below detection thresholds. However, this would also mean it would not be detectable near Mars, the claimed origin point of the social media reports. Could the signals have been intermittent, brief bursts that were missed? This is also a possibility. Radio observations are not continuous. Telescopes have finite observing time, and their aim might not always be directed at the precise location at the opportune moment. A short-duration burst could potentially elude detection. Nevertheless, the absence of any independent corroboration is a significant red flag. If these pings were indeed real, multiple observatories should have registered them by now. The fact that none have done so suggests the claim is unsubstantiated. Let us now consider the plausibility from an engineering perspective. Assuming 3I Atlas is an artificial probe, what would be required to transmit a 1.4 gigahertz signal detectable across interplanetary distances? Radio transmission necessitates both a power source and an antenna. The power output depends on the transmitter's design and its energy supply. The efficiency of an antenna is determined by its size relative to the signal's wavelength. At 1.4 gigahertz, the wavelength is approximately 21 centimeters. A reasonably efficient antenna could measure a few meters in diameter, a size easily accommodated on a spacecraft. If the probe possesses a nuclear power source or another long-term energy supply, generating a few watts or kilowatts of radio power is technically feasible. This would be sufficient for detection at distances of millions of kilometers, provided a sensitive receiver and a directional antenna are employed. However, natural phenomena can also produce radio emissions. Comets, during their interaction with the solar wind, can generate plasma instabilities that emit radio waves. Lightning, or indeed dust clouds if present, could potentially produce broadband radio bursts. While rare, these occurrences are within the realm of possibility. Therefore, even if a radio signal were detected originating from 3I Atlas, it would not automatically confirm the object's artificial nature. A detailed analysis of the signal's structure would be imperative, searching for characteristics such as modulation, repetition, frequency drift, or any other attribute suggesting encoded information rather than random noise. What should we anticipate in the coming weeks? Upcoming radio astronomy observation campaigns are specifically targeting the regions surrounding 3I Atlas. Multiple observatories are coordinating their efforts, covering various frequency bands and observation times. Data release schedules are expected to provide results in late 2025 or early 2026. SETI organizations are also actively monitoring the situation. Breakthrough Listen has officially added 3I Atlas to its target list. If any anomalies are present in the radio spectrum, they are highly likely to be detected. The function of radio astronomy in this investigation is to either substantiate or refute the technosignature hypothesis. If, despite thorough monitoring, no signals are detected, the claim will be definitively dismissed. Conversely, if signals are detected and subsequently verified, the scientific discourse will undergo a profound transformation. Radio astronomy also serves as a potent tool for debunking claims. Numerous alleged anomalies, ranging from fast radio bursts initially suspected to be alien transmissions to mysterious pulses later revealed to be caused by microwave ovens in observatory cafeterias, have been definitively explained by natural or human-induced sources. The field inherently fosters a culture of skepticism and rigorous verification. Regardless of whether Three-Eye Atlas is a natural phenomenon or an engineered artifact, radio astronomy stands as a frontier technology for discovery. For the present moment, the silence emanating from the object carries more weight than any purported pings. We shall now conclude this investigation, summarizing our findings and outlining the anticipated developments for late 2025 and early 2026. This is Part 15, Wrap-Up and What's Next in late 2025, early 2026. Let us consolidate our understanding. Our inquiry commenced with a dramatic assertion that Three-Eye Atlas might be on a trajectory to intercept Earth. This claim was ostensibly grounded in factual data, specifically a reported non-gravitational acceleration of 0.02 millimeters per second squared, and a straightforward calculation demonstrating that 50 days of such sustained acceleration could result in a velocity change of 86 meters per second. The arithmetic is indeed correct, and the underlying data are valid. However, the extrapolation, the leap from the existence of an acceleration to the conclusion of a targeted interception, hinges upon unverified assumptions. The acceleration would need to be persistent, precisely directed, and timed to coincide with Earth's orbital position at an exact moment. None of these conditions have been established. We have meticulously examined the object's trajectory and its predicted missed distance. Official sources indicate that Three-Eye Atlas will pass Earth at an approximate distance of 1.88 astronomical units, equivalent to about 270 million kilometers, on December 19, 2025. This distance is exceptionally vast. To achieve an intercept trajectory from this vantage point would necessitate a significantly greater velocity alteration applied over an extended period with extremely precise timing. The available data do not support the assertion of an Earth alignment. We have thoroughly explored potential natural explanations for the observed acceleration. Outgassing, the process of ice sublimation generating propulsive thrust, remains the primary hypothesis. However, the required rate of mass loss is substantial, amounting to at least 1/16 of the object's total mass over a period of 1 month. If Avi Loeb's calculations are accurate, this process should produce a significant coma, a phenomenon that telescopes have not yet definitively observed. The jury is still out on this matter. We have also entertained more speculative hypotheses. Could Three-Eye Atlas be an artificial construct, a probe dispatched by an extraterrestrial civilization? The observed acceleration, its estimated size, and its trajectory all raise intriguing questions. Yet there is no definitive evidence, no smoking gun, no detected radio signals, no signatures of non-volatile propulsion, no irrefutable proof. The hypothesis, while captivating, remains speculative and unproven. The narrative disseminated on social media amplified the initial claim, transforming a scientific anomaly into a sensational story of alien interception. This narrative spread with remarkable speed, eclipsing the scientific explanations and blurring the distinction between raw data and interpretation. It serves as a stark reminder of how information propagates in the contemporary digital age, how uncertainty can devolve into spectacle, and how the human inclination for pattern recognition can lead to dramatic, albeit unsubstantiated, conclusions. We have also considered the implications of a worst-case scenario. If the object were indeed to intercept Earth, the consequences would be catastrophic, potentially an extinction-level event. However, the chain of assumptions required to reach this conclusion is exceptionally long and fragile. Such a scenario would demand capabilities, intent, and timing from the object that push the boundaries of plausibility. Furthermore, we have broadened our perspective, contextualizing 3I Atlas within wider trends in space science. Advancements in exoplanet atmosphere imaging, research into dark matter, AI-driven orbit prediction, and radio astronomy all contribute to a richer understanding of this phenomenon. This is not merely an isolated incident concerning a single object. It is emblematic of how we study the universe, how we detect anomalies, how we interpret complex data, and how we prepare for the unexpected. Therefore, what are the key takeaways from this investigation? Firstly, 3I Atlas represents a rare interstellar visitor holding significant scientific value regardless of its origin, whether natural or artificial. Secondly, the mathematical calculation supporting the 86 meters per second velocity change is accurate, but it does not, in itself, imply an imminent Earth impact. Thirdly, several critical unknowns persist. The precise vector of the acceleration, its continuity, and its temporal correlation with Earth's orbital position. Fourthly, observational data expected in late 2025 are paramount. Measurements of mass loss, refined astrometric residuals, spectroscopic analysis, and radio monitoring will collectively clarify the object's nature. Fifthly, while worst-case scenarios are dramatic, they rely on numerous unverified assumptions, and official agencies maintain that there is no current threat. Sixthly, diverse fields of scientific inquiry converge on 3I Atlas, positioning it as a focal point for multiple lines of investigation. Let us now consider the timeline. Perihelion, the point of closest approach to the Sun, occurred around October 30th. The object has now passed its nearest solar point and is proceeding outbound. November marks the commencement of intensified observation campaigns. The object is emerging from the Sun's glare, becoming increasingly amenable to observation. December 19, 2025 is designated as the date of closest approach to Earth. This is the pivotal moment, the date referenced in the social media claims. By this time, we will possess several weeks of additional observational data. Early 2026 will witness the object's outbound trajectory, potentially including a distant flyby of Jupiter around March. Following this, 3I Atlas will recede from view, moving deeper into the outer solar system and eventually returning to interstellar space. What should you, the informed observer, watch for? Keep abreast of official orbital updates from NASA, ESA, and other space agencies. Look for refined calculations of the missed distance and any subsequent adjustments to the trajectory. Pay close attention to spectroscopic results. Are volatiles detected? Is there evidence of a coma? Does the object's color continue to exhibit unusual characteristics? Monitor imaging reports. High-resolution images from instruments like the Hubble Space Telescope or the James Webb Space Telescope may reveal surface features, discernible jets, or other structural details. Track announcements from radio observatories. Any confirmed signal detections at 1.4 GHz or other frequencies would constitute major news. Furthermore, observe the discourse between media narratives and scientific statements. How do mainstream outlets frame the story? Do they prioritize caution or sensationalism? How do scientists respond to the assertions made on social media? This interplay between public perception and scientific rigor is an integral part of the unfolding narrative. If no dramatic developments emerge by early 2026, what then? Does this definitively invalidate the maneuver claim? Almost certainly. If the object behaves in a manner consistent with a comet, exhibiting predictable outgassing that diminishes as it recedes from the Sun, if its acceleration decreases or ceases, and if no radio signals are detected, then the natural explanation will prevail. 3I Atlas will then join the ranks of other interesting yet ultimately conventional interstellar visitors. However, should anomalies persist, if the acceleration continues even far from the Sun, if mass loss remains minimal despite the observed thrust, or if radio signals are detected, then we are faced with a genuine enigma. In such a scenario, the exotic hypotheses would transition from mere speculation to subjects demanding rigorous scientific investigation. Will 3I Atlas settle into the category of an interesting but natural object, or will it become the first unequivocally confirmed engineered interstellar probe? The answer will not be found in speculative social media pronouncements, but through dedicated observation by telescopes, rigorous analysis of data, and the diligent work of scientists engaged in measurement, analysis, and interpretation. One final reflection. The universe does not inherently cater to our comfort. It is indifferent to whether we are prepared for its revelations. For centuries, humanity has progressively learned that we are not unique, not central, and not cosmically solitary. Every significant discovery has contributed to a broader sense of humility. 3I Atlas, irrespective of its eventual classification, represents another step on this ongoing journey of understanding. If it proves to be a comet, we will have gained further insight into the diversity of interstellar travelers. If it is something else entirely, we will have learned that the galaxy is far more complex and potentially more populated than we previously imagined. In either case, this object serves as a potent reminder to gaze upward, to remain inquisitive, to question our assumptions, and to prepare for possibilities we have yet to conceive. The investigation is far from over. It is, in many respects, just beginning. The forthcoming months will determine whether the social media claims were flights of fancy or indicative of a more extraordinary unfolding. By early 2026, we will possess a clearer understanding. Until then, observe the celestial expanse. The universe is watching us in return.